American Airlines Flight 191, the maintenance shortcut that killed 273 people and grounded every DC-10 on Earth. Captain Walter Lux was one of the most experienced DC-10 pilots in the world. He had thousands of hours in the aircraft. He knew its sounds, its rhythms, its behavior at every phase of flight. He was, by every professional measure, exactly the kind of man you wanted in that seat. When something went wrong, and it didn't matter. Flight data recovered from the wreckage would later prove, with cold mathematical certainty, that from the moment American Airlines Flight 191 began its takeoff roll at Chicago O'Hare on the afternoon of May 25, 1979, Captain Lux had approximately 1.2 seconds between the first sign of catastrophic failure and a point of no return from which no human being with any amount of skill, training, or courage could have recovered. 1.2 seconds. He wasn't slow. He wasn't distracted. He wasn't impaired. He was a professional doing everything correctly inside a machine that had already been broken, not that afternoon, not on the runway, but weeks earlier in a maintenance hangar in Tulsa, Oklahoma, by a decision that saved American Airlines roughly $200 per aircraft per maintenance cycle. $200. 273 people died on that runway apron, in that cornfield, in that fireball visible from downtown Chicago. This is not a story about a plane crash. This is a story about a chain of decisions, financial, regulatory, institutional, made by people who understood the risks, weighed them against the costs, and kept flying anyway. Flight 191 was not a surprise. It was an invoice, finally, catastrophically, coming due. If stories like this grip you, if you want to understand not just what failed, but why and who and how the same logic is still operating right now, subscribe to System Failure. New documentary every week. The button is right there. It costs you nothing. It might cost you some sleep. To understand how 273 people died over a cornfield north of Chicago, you have to go back further than May 1979. You have to go back to the DC-10 itself, what it was supposed to be, and what it repeatedly proved itself to be across nearly an entire decade of warning signs that the aviation industry treated as acceptable losses. The Douglas DC-10 was born from competition and ambition. In the late 1960s, American Airlines issued a challenge to the American aerospace industry: build a wide-body, high-capacity jet that could operate out of airports with shorter runways than those required by the Boeing 747. The market was enormous. The stakes were company-defining. McDonnell Douglas answered with the DC-10, a wide-body Triget, 2 engines under the wings, one mounted at the base of the tail, capable of carrying over 200 passengers in a single configuration, with range and performance that promised to reshape domestic and international aviation. It entered service in 1971. It was modern, capable, and commercially successful, and within a year, it was already trying to kill people. In June 1972, American Airlines Flight 96, a DC-10, was cruising at altitude when the rear cargo door blew out. The decompression was violent. The floor of the passenger cabin partially collapsed. Flight controls were damaged. By what investigators would later describe as something close to a miracle, the captain managed to land the aircraft. Nobody died. The problem was specific and already understood. The cargo door locking mechanism was poorly designed. Under certain conditions, it could appear locked while remaining dangerously compromised. McDonnell Douglas knew about the vulnerability. The FAA knew about it. What followed was not a mandatory airworthiness directive, the regulatory instrument that would have compelled every operator to fix the problem immediately. What followed was a gentleman's agreement, an informal service bulletin. McDonnell Douglas lobbied against mandatory action, arguing the fix could be implemented voluntarily without the commercial disruption of a formal order. The FAA agreed. The fix was not universally applied. In March 1974, Turkish Airlines Flight 981 departed Paris-Orly with 346 people on board. The rear cargo door, carrying the same design flaw, inadequately addressed after Windsor, blew out at altitude. This time, there was no miracle. The floor collapsed. Flight controls were severed. The aircraft entered an uncontrollable dive and struck the ground at approximately 490 miles per hour in a forest outside Paris. There were no survivors, 346 people. It remains to this day one of the deadliest single aircraft disasters in aviation history. And what happened after Paris? The DC-10 kept flying. McDonnell Douglas issued fixes. The FAA mandated specific corrective actions. The aviation industry conducted the familiar theater of post-disaster response: investigations, recommendations, modifications, and then return to business. Airlines had DC-10s on order. Routes depended on them. Schedules were built around them. The economic infrastructure of commercial aviation had integrated this aircraft deeply enough that removing it felt unthinkable. There is a phrase that investigators use when describing this kind of institutional response. They call it normalization of deviance, the process by which warning signs, near misses, and even moderate disasters become absorbed into normal operations. Each incident that doesn't cause a catastrophe becomes evidence that the risk is manageable, that the system is resilient enough, that the calculus still works. The DC-10 had killed 346 people in a French forest, and the calculus still worked. So when maintenance crews at American Airlines began developing a faster, cheaper way to remove and reinstall the DC-10's wing-mounted engines, a method that saved time, saved money, and had not been explicitly prohibited by any regulatory authority, that decision existed within an institutional environment that had already demonstrated repeatedly its capacity to absorb warning and continue operating. $200 per aircraft per maintenance cycle. It doesn't sound like a number that kills people. It does. To understand the maintenance procedure that destroyed Flight 191, you need to understand what changing an engine on a DC-10 was supposed to look like and what it looked like instead. The approved method, as specified by McDonnell Douglas, was methodical and sequential. Remove the engine first, then remove the pylon, the structural mount connecting the engine to the wing, reinstall the pylon, then reinstall the engine. Two separate operations requiring separate equipment setup, separate procedures, separate time. American Airlines engineers looked at this process and identified what seemed in isolation like a reasonable efficiency. If you could remove the engine and pylon together as a single unit, using a forklift to support the combined weight during extraction and reinstallation, you could eliminate one full phase of the procedure. You saved time. You reduced the number of equipment configurations. You kept the aircraft out of the hangar for less time and returned it to revenue service faster. The combined weight of a CF6 engine and its pylon was roughly 14,000 pounds. A forklift could manage that weight. What a forklift could not manage, what no forklift operated by any crew could reliably manage, was the micro-level of precision required to support that combined unit without introducing stress into the components that connected them, specifically into the aft bulkhead of the pylon, into the flanges, into the structures that were engineered to tolerate the stresses of flight, not the stresses of being improperly supported on shop equipment during removal. McDonnell Douglas had not designed the pylon to be handled as part of a combined unit. The structural assumptions built into those components presumed they would be separated during maintenance work. When they weren't, when the forklift method introduced lateral loads and stress concentrations, the pylon was never meant to absorb, the damage was invisible. It hid inside the metal, microscopic cracks in the aluminum, barely measurable with standard inspection techniques, growing incrementally with each subsequent maintenance cycle, each flight, each pressurization and depressurization cycle, each thermal expansion and contraction over thousands of hours in the air. American Airlines wasn't the only carrier using variations of this approach. The logic was industry-wide. Find efficiencies, reduce downtime, keep the aircraft flying. The FAA had not explicitly approved the forklift method, but it had not explicitly prohibited it either, and in the regulatory environment of the 1970s, that ambiguity was effectively permission. The pylon on the number 1 engine of the DC-10, registered as Flight 191, had been through this process. The cracks were there. On the afternoon of May 25, 1979, 271 people boarded American Airlines Flight 191 at Chicago O'Hare International Airport. The aircraft was bound for Los Angeles. The day was clear, visibility was excellent. The crew, Captain Walter Lux, First Officer James Dillard, and Flight Engineer Alfred Udovich, were experienced, current, and prepared for a routine transcontinental flight. At 3:02 in the afternoon, Flight 191 began its takeoff roll on runway 32 right. V1, the decision speed beyond which a takeoff cannot safely be aborted, came and went. The aircraft rotated, the nose lifted, and then at approximately 145 knots and 35 feet above the runway surface, the number 1 engine, along with its pylon, along with the 3 inches of wing leading edge it tore away on its way out, separated from the left wing and tumbled over the top of the aircraft, falling behind and to the left on the runway. Passengers on the right side of the aircraft saw it happen. Several of them were photographers and journalists. Some of them captured it for Captain Lux and his crew. There was no view of what had just occurred. There was an aircraft that had suddenly, violently become something different from what it had been 2 seconds earlier. The 1.2 seconds began. What followed in those seconds was not chaos. It was, in the most terrible sense, physics. When the engine separated, it did not simply remove thrust from the left side of the aircraft. It did something far worse. As it tore free, it severed hydraulic lines running through the leading edge of the left wing. Those lines fed the slat system, the movable leading edge surfaces that, when extended, increase the wing's lifting area and allow the aircraft to fly safely at lower speeds during takeoff and landing. The slats on the left wing retracted. The slats on the right wing remained extended. This asymmetry, 2 wings in fundamentally different aerodynamic configurations, created an imbalance in lift that began rolling the aircraft to the left. The crew's instruments lost power. The stick shaker, the device that physically vibrates the control column to warn pilots of an approaching aerodynamic stall, went offline. The stall warning system, which should have been screaming at them, was silent because it had no power. There is a procedure for engine failure on takeoff. Pilots train for it constantly. The instinct is to maintain airspeed, to push the nose down slightly to prevent a stall, to keep the aircraft flying fast enough that the remaining engines can sustain flight. Captain Lux followed this instinct. He pushed the nose down. In a normal engine failure scenario, this was correct. In this scenario, it was the worst possible response, through no fault of his own, because the aircraft was not experiencing a normal engine failure. It was experiencing progressive left-wing stall, invisible to him without stall warning, invisible to him without his instruments, in an aircraft that was now asymmetrically unflying the left wing with every passing second. Reducing pitch to maintain airspeed on the right wing only deepened the stall on the left. The aircraft rolled past 90 degrees of bank. It continued rolling. The nose dropped below the horizon. Flight 191 impacted a trailer park and open field approximately 40,400 feet from the runway threshold at roughly 300 miles per hour. The fireball was visible from miles away. There were no survivors on the aircraft. 2 people on the ground were also killed. 273 total. It remains the deadliest aviation accident in United States history. The investigation that followed was, in many respects, the most important piece of the entire story because of what it initially focused on and what that focus revealed about how aviation institutions, even in the immediate aftermath of catastrophe, default to protecting themselves. Early NTSB attention fell on the crew. There were questions about whether the pilots had responded correctly, whether their training had been adequate, whether the decision to reduce pitch, the instinct that physics had turned into a fatal action, represented a procedural failure. This framing was not surprising. It was the familiar architecture of aviation disaster analysis. Find the proximate cause, identify the human at the closest point of failure, describe what they should have done differently. It was also, in this case, almost completely wrong. The flight data recorder, the cockpit voice recorder, the trajectory analysis, and the aerodynamic modeling all converged on a single conclusion. Given the specific combination of failures that occurred on Flight 191, engine separation, simultaneous hydraulic loss, simultaneous slat retraction, simultaneous loss of stall warning, all within the same instant. There was no procedure in the American Airlines training manual, no procedure in the FAA-approved DC-10 operating guide, and no humanly achievable reaction time that would have allowed the crew to diagnose and correctly respond to what was happening before the aircraft became unrecoverable. The crash was locked in before the plane left the ground. Locked in not on the runway, not in the weeks before, during final maintenance checks. Locked in a hangar in Tulsa during a procedure that saved $200 that nobody had explicitly prohibited, that an entire industry had normalized into routine. The FAA grounded every DC-10 in the United States on June 6, 1979, 12 days after the crash, following the discovery of similar pylon damage on other aircraft. It was the first time the FAA had ever grounded an entire aircraft type based on maintenance concerns rather than a specific design defect. The grounding lasted 37 days. During those 37 days, American Airlines alone lost an estimated $40 million in revenue. Industry-wide losses exceeded $100 million. International aviation authorities followed the FAA's lead. The DC-10 was temporarily removed from the sky across much of the world. When it came back damaged, not structurally but reputationally. Passengers were afraid of it. Travel agents booked around it. Airlines that operated fleets built around the DC-10 found themselves commercially exposed in ways they hadn't anticipated. Orders slowed. McDonnell Douglas, which had already been losing ground to Boeing on multiple fronts, found its flagship wide-body aircraft carrying a stigma it could never fully shed. The DC-10 would continue flying for decades in freight operations and military variants in configurations far removed from the premium passenger routes it was designed to serve. But as a commercial passenger aircraft at the center of American aviation, it never fully recovered. McDonnell Douglas never fully recovered. In 1997, after years of declining market share, financial pressure, and the accumulated weight of an industry that had moved on without them, McDonnell Douglas was acquired by Boeing, an American aerospace company, one of the companies that had defined American aviation since the propeller age, ceased to exist as an independent entity. The lineage is direct: the forklift in the hangar, the cracked pylon flange, the fireball north of Chicago, the grounded fleet, the lost orders, the Boeing merger, $200 per maintenance cycle. What do you do with a story like this? What is the correct response to a system that produced in sequence a design flaw in 1972, a warning in the form of 346 dead in a French forest in 1974, a maintenance shortcut that nobody prohibited, and a final bill of 273 lives in 1979. The aviation industry's answer in the years after Flight 191 was structural. The FAA revised its authority over maintenance procedures, closing the ambiguity that had allowed the forklift method to exist in regulatory gray space. Inspection requirements for pylon attachment structures were made more rigorous. The doctrine of how an engine could be removed was codified explicitly, not left to engineering teams to optimize for efficiency. These were the right answers. They were also the answers that arrived after the invoice. The harder lesson, the one that aviation has learned better than almost any other industry, but still imperfectly, is that warning signs are not random. Near misses are not luck. When a system produces a close call and then continues operating without fundamental change, it is not demonstrating resilience. It is demonstrating the early phases of an accident sequence that has not yet reached its terminus. Windsor, 1972, Paris, 1974, Chicago, 1979. The DC-10 told the same story 3 times. The first 2 times, the industry found ways to hear it as something else. The third time, there was no reframing available. 273 people were in a cornfield north of Chicago. Captain Walter Lux, who had done nothing wrong, who had done everything a human being could do, who had been betrayed by the machine and the system and the economics long before he ever strapped in that afternoon, was among them, the most unset,